All right, let's talk about Chapter 6.3, Inverse Trigonometric Functions. And let's start with the inverse sine function here. The inverse sine function, y equals the inverse sine of x, means that x equals sine y. We'll talk more about inverses in just a moment. The inverse sine function is sometimes called the arcsine function and is notated arcsine of x. Note that y equals the inverse sine of x. It has domain -1 to 1 and range -π/2 to π/2. And this first example here asks me to explain the domain restriction for the inverse sine function. So the thing that we need to remember about inverse functions in general is, first off, they undo each other, and second, they have this relationship, which I'll write over here. If you have a function, f, and you plug into it its inverse, f inverse, and this is from the first part of a pre-calculus class, what they do is these basically undo each other. You can think of it as they undo each other and you get x. That is, if they are inverses. And it's the exact same thing as plugging this into this, like that. So whether you plug f into its inverse or its inverse into itself, you get the input, x, whatever that is, out every time, no matter what you plug in. Okay? That is the necessary and sufficient conditions for a function to have an inverse. We've seen functions and their inverses before. The most easy example of that would be x squared, okay, and the square root of x. So we know that x squared, and if you take its square root, well, that's just x. And we know that that's exactly the same thing as just taking the square root of x and squaring it. Either way, it's the same. They cancel each other, and you just get x out. Therefore, these two functions are inverses. But we also know something about the graphs of each one of these functions, and I want to talk about it. Because x squared, we know that x squared has a graph that looks something like this. It's a parabola. Okay, and I'm not going to label anything, so this is technically correct. Okay, so that's x squared, and that's fine. That's a function. Because remember, when we're dealing with inverse functions, we want the inverse function to be, well, a function. Well, in order for it to be a function, it has to pass the vertical line test, which, of course, x squared does. Okay. However, if we were to graph all of square root of x, which is normally a plus or minus, it's what we've been dealing with for the past couple of weeks. You normally get plus or minus square root of x is the whole thing. And let me show you plus or minus square root of x. Okay, here's plus square root of x. Okay, and I'm going to do minus square root of x in a different color. Okay, there's minus square root of x. If you considered that as one function, this wouldn't be a function, would it? Because it fails the vertical line test there. So what we do is we divide it into two halves, the plus half and the minus half, like that. And because we do that, each part of this passes the vertical line test. This one up here only touches here, so that's the positive or the principal branch of the square root, as it's called by big nerds. And then down here, it only touches here on the negative square root. So we actually had to split it in half. And what we did with the sine function to find its inverse is this. We just said, okay, well, we've got a x and y axis here, and we have the sine function. So the sine function does something like this. So here's π/2, here's pi, here's 3π/2. I'm not going to draw it any further than that because we don't need it. Negative π/2. Here is negative pi. I don't even need it further than that, but just to be symmetrical, negative 3π/2. Okay, now let's draw the sine function. So the sine function is 1 up here and is -1 up here, and it goes up to this point and down to this point. So the sine function in red is going to look something like this here. So it's going to come up to this point, and then it's going to come back down, and it's going to do its thing, and I'm just going to leave it alone from there. We'll see why in a second. And it's going to come down to here, and then it's going to come back up All right, and it's going to do its thing, and we're going to leave it alone. Probably could draw that a little bit better. Hang on. Let me go ahead and get that, and then it's going to do its thing. There we go. Something like that. So the thing is it's going to have this exact same sort of behavior overall, because we need to choose a part of this to be the inverse. It's the exact same reason that the square root needed to be chopped in half. We can't take this whole thing. If we took all of the sine function, like literally all of the sine function, and we made it its inverse would look something. It would go between -1 and 1, right? Literally take this entire graph, make the x-axis the y-axis and the y-axis the x-axis. Rotate it 90 degrees clockwise, counterclockwise, your choice. Both of them work for this example. It would look something like this. And it would just keep going on and on forever. And that very clearly fails the vertical line test an infinite number of times. Because inverses, the inverse of a graph is just rotate the graph, mirror it over, well, this line actually, but it would end up looking like this, and we don't want it to look like this. So we have to take just a little tiny chunk, and what we do is we say, okay, fine, we're going to take a little tiny chunk, and it's going to be the chunk right here to right here. So -pi/2 to pi/2. That's what we set up here. So we said it has range -pi/2 to pi/2. So what we took in our domain in the original function, that's the sine function, becomes our range over here, because that's how inverses work. They flip domains and ranges. So this thing is going to go between -pi/2 and +pi/2, which means that when you do the arcsine function, you will never get out an answer that's anywhere other than -pi/2 to +pi/2. All right, and we'll talk about this in terms of the unit circle in just a second. And it has a domain from -1 to 1 because that was the range of the sine function. Okay, and when you end up drawing this function, it ends up looking kind of weird, and it isn't even a graph that I need you to know what it looks like. And I'm not even going to try to burden you with the knowledge of the graph. If you want to know what the inverse sine function's graph looks like, it's really, really weird. You're more than welcome to go look it up. It's a strange looking graph. But the thing to remember about this is that we had to restrict its domain so that it wouldn't do this kind of stuff and fail the vertical line test, and that this information up here. So it has domain -1 to 1, which means you cannot plug a number smaller than -1 or larger than -1 into it. It'll break the function. And it only gives out answers between -pi/2 and +pi/2. Now let's think about that in terms of the unit circle real quick. And let me draw a potato here. So if you imagine that amazing circle right there is the unit circle, what we're talking about is it'll only go from +pi/2 to -pi/2, which goes back this way. -pi/2. And we'll talk about what's going on here later, but it'll only give you answers. Arcsine only gives answers in quadrants 1 and 4, and that's definitely worth noting somewhere. Arcsine only spits out answers in quadrants 1 and 4. You can't get answers over here. Yet, the questions are going to ask you things like, find all values of sine theta equals √5/7 between 0 and 360 degrees, or between 0 and 2 pi. Well, you need to also get the answers that are over here if there are answers over here. But the arcsine won't give it to you. So we've got to do some reference angle stuff and some jumping around the unit circle math. But we've done that before. It's no big deal. But that is the inverse sine function and where it comes from. Now I'm going to do the exact same thing for the cosine function, but it's going to be an awful lot quicker because it's the exact same thing as the sine function, just slightly different. So we're going to go ahead and look at that. So the inverse cosine function, y equals inverse cosine of x. Okay, it means x equals cosine y. That is, if you solve this equation, just like you could with the sine, you just take the cosine of both sides, you'll get this second equation down here. So the inverse cosine function is sometimes called the arc cosine function and notated arc cosine x. I prefer this notation. It's just easier to write, easier to type. Notice that y equals inverse cosine of x has domain -1 to 1 and range 0 to pi. So the domain's the same for the arc cosine and the arc sine function, because the range was the same for the sine and cosine function, respectively. However, the range of the inverse cosine function, we chose to take a different part of it. And I'll show you the part that we chose to take. So here is a xy axis real quick, and here is the cosine function from 0 to pi. So here's 0, here's pi over 2, and here is pi. And the reason that we take it like this, here's 1, here's -1, that's everything you need to draw when you're going to do this. And then here is the cosine function. The cosine function, of course, starts up here, it goes to here, and then it goes to here. And I'm going to continue drawing it in both directions afterwards. But we wanted to take a section of the graph, and it was the same thing for the sine function, that has both positive and negative parts to it, because we want to be able to get out positive and negative angles. Well, if you only took between, you don't have to draw this part, but if you only took between -pi/2 and pi/2 like we did for sine, like if you only took things between these two lines, you would only have positive values. And that's not useful. We need to be able to get out negative values. We could have arbitrarily taken this, but would it have worked as a function? Ponder that for a moment, and you may figure out why we didn't do that. But also, we'd like to be able to get negative values. So this is what we took, and if you want to know what this thing's graph is going to look like, just rotate it yield that way, and that's more or less right. It's a very strange looking graph, about 90 degrees. So turn your head to the right and stare at that, and flip your domains and your ranges, and that's about dead on. So that's the domain restriction for the inverse cosine function. It's exactly the same way. If you take the entire cosine function, it's going to look like that, and it will, of course, fail the vertical line test. So we need to take a section that's going to work for us, and the easiest section to take is just 0 to pi. We just took the easiest ones we could do. We could, of course, have taken pi to 2 pi, or 2 pi to 3 pi. We could have taken any interval of pi. We could have taken -pi to 0 if we felt like, but that's like dumb. So remember that the inverse cosine has domain -1 to 1. That means you cannot plug in a number smaller than -1 or bigger than 1. I'll try to get you with that later. Okay. Also, try and remember that the range is 0 to pi. You're only going to get out things in quadrants on the unit circle. So here's your unit potato, and quadrants 1 and 2, because that's 0 to pi right there. Okay, so 0 to pi is only going to give you out quadrants 1 and 2. So the thing to remember that you should probably write down is that the arc cosine function gives us things back in Q1 and Q2. That's where all of our answers are going to live. Of course, that's where 0 to pi is. And you may want to go back up in your notes if you haven't already written it down. Write it with the rest of your stuff for arcsine. But it'll only give you back things in Q1 and Q4. You may notice that neither one of these things give us anything in Q3. There are no answers there. How about that? So just keep that in mind. Arc cosine is going to give you things in Q1, Q2. Arc sine is going to give you things in Q1, Q4. And that's going to help us solve things. So let's move on. There's one more of these. We're just going to do the one for tangent. And then we're going to just do a whole bunch of examples. And you're going to find that they're really easy, and we've been doing them all along. Just using this relationship, that y equals the inverse cosine just means x equals cosine y. You've been doing it in this form. This is the one where you just look it up on your sheet. You have cosine theta equals √2/2. Well, just go look that up. It's two different places. And that's what we're going to be doing with this, except now I'm going to be able to show you how to use those buttons on your calculator in whatever program or calculator it is that you use to figure these things out, because you do need a calculator for these if they're not standard angles. So let's just move on. So let's talk about the inverse tangent function. It's the last one, and it's the one that I'm actually going to draw a graph for. So the inverse tangent function, y equals inverse tangent of x. It means that x equals tangent y, and that's always how that works. Okay. The inverse tangent function is sometimes called the arctangent function and is notated arctan x. Now this is the one that you see a lot more often in calculus and in Cal 2 moving forward, because its domain is so nice. Its domain is anything you want to. You can plug anything you want to into an inverse tangent function, because the range of the normal tangent function turned into the domain in the inverse tangent function, and the range of the tangent function was everything. So There is no domain restriction for the inverse tangent function, but your range is between negative pi over 2 and pi over 2. So let me show you real quick what this graph looks like. So, of course, to draw a graph, I'm going to need to do some of this. So there is no domain restriction for the inverse tangent function for the very simple reason that the range was infinite. The range was all real numbers for the normal tangent function. So we didn't have to take any part of it and chop it off. However, we are just going to take that single period between negative pi over 2 and pi over 2. It was in the middle of the graph, like that. And the inverse tangent function is going to approach asymptotes at each one of these points. So let me draw the asymptotes here. And it's going to look something like this, roughly. It's going to approach that forever that way, and it's going to approach it forever this way. That's a graph worth knowing. So that is the inverse tangent function. I don't have to label anything on the x-axis because it's infinite in both directions. So this is the function f of x equals arctan x. If you prefer, it's exactly the same thing as the inverse tangent of x. They're just alternate notations for the same thing. So arctan x, inverse tangent of x. I just prefer arctan x and the arc functions just because they sound cooler, first off. And it also gets a little less confusing because we sometimes do things like tangent squared x that we've seen before. And you need to know that this means inverse, not 2. Well, not a power. And if you just use this, it gets rid of all of that. So I prefer and would prefer if you used this. You may see it used the second way elsewhere. Just remember that means inverse tangent. And of course, this is sort of an aside, but think about this. This is wrong, but think about this. If this meant tangent to the negative first of x, anything raised to the negative first is just 1 over that thing. So this would technically be, if it meant this, it doesn't, that's why I'm writing it in red, but if it did, it would just be 1 over tangent to the first of x. But this is just cotangent. We don't write tangent inverse to mean this because we would just write cotangent. In case you were wondering, don't put that in your head. Use this notation, it's just better. If a problem is given to you like that, then you should probably use that notation. Otherwise, just use this notation to talk about inverse functions. So let's move on and talk about some relations, and then let's just do a whole bunch of examples, and we'll be done. So let's talk about some relations for the inverse sine, cosine, and tangent functions. So note the following. For angles in the interval negative pi over 2 to pi over 2, if sine y equals x, then sine inverse of x equals y. It's the same thing for the interval of 0 to pi and for negative pi over 2 to pi over 2 for cosine and tangent respectively. So the way that this works, and all that this is saying, is that you can solve for variables. You can solve for variables using this. And let me show you this one here and this next example. Let me show you what this is saying. So for all angles in one revolution of the unit circle, that's what that means. It says find all the angles that solves the equation cosine theta equals root 3 over 2. Now, you recognize this as a problem that you've done before. This is, go look it up on your sheet. You've done that before. But I want to show you, I want to use this little property right here. If cosine of y, which is theta in our case, equals x, then the inverse cosine of x equals y. This just says we can take the inverse cosine to get rid of a cosine. That's what it says. It also says, if I'd written it a little better, cosine y equals x if and only if cosine inverse x equals y, which is technically slightly less right because of domain restrictions. Don't worry about it too much. These are, if everything works out right over here, those are swappable. So what I mean by that is this. That's just a lot of talking to say this. We have that. This is another way to do this. If you don't even want to use your sheet, here's another one. So root 3 over 2. What this is saying is we have that the cosine of something equals something else. We have it in that form. It's saying then that we can just take the inverse cosine of both sides. So the inverse cosine. Now I'm going to write arc cosine. So the arc cosine of both sides. the arc cosine of the cosine of theta equals the arc cosine, I took the arc cosine of both sides, the arc cosine of negative root 3 over 2. All right? So, in order to solve this, we notice first off that this property holds. This property right here holds, and it says that arc cosine and cosines cancel. So that's going to leave us with the equation theta, the arc cosine and the cosine cancel. Just like a square and a square root cancel, just like a e and a natural logarithm cancel, just like any function in its inverse cancels, arc cosine and cosine cancel each other. If everything works out, that's what it's saying, for angles in this interval. So, we're going to get the arc cosine of negative root 3 over 2. Okay? So the one thing that you have to make sure of every single time you're doing this, and your calculator will tell you if this doesn't work out, is this number, is negative root 3 over 2, is this number in the interval from negative 1 to 1? That is that number between negative 1 and 1. So let's hop on our calculator and look at it real quickly. So we want to know, first off, does negative root 3, so does negative square root of 3 over 2, is this number between negative 1 and 1? Well, yeah, it's negative 0.08, so it's a fraction. I mean, it's a, well, it is a fraction. It's a proper fraction. But it's also a number that has a 0 out here in its leading ones place. So yes, it is a fraction. So it's going to work. So what we want to know is, what is the arc cosine of this? So I'm just going to cut that real quick. And let me show you how to use this. This is on Delta Math. And in the top right-hand corner of your screen, if you click on the little calculator button, it'll give you this. And you'll notice there is no inverse sine function on here, because you've got to click the functions button. Note very carefully, look here at the functions button as I click it. It changes to the back button, so if you want to go back, you just click that button again, and that'll toggle between them. So let's go here. Right here is the inverse cosine function. So click it, and it'll open it up for you. And now I'm just going to paste the value that I previously cut, and it's going to tell me that it's 150. So 150 what? Radians or degrees. Look down here, it's in degrees. So if I asked for it in degrees, this would be correct, 150 degrees. So 150 degrees is the answer. You could also look it up in radians. This isn't going to be terribly useful for you, because it's going to give you 2.6. 2.6 radians doesn't mean a lot to you, right? Which is the reason why this thing asks you a lot of your questions in degrees. This actually has the pi multiplied into it. If you want to know what it is in terms of not pi, you would have to, well, divide the pi out. So divide the pi out, you get 0.83333. And if you know what this thing is as a fraction, you can figure that out. But Mr. Bryant, you say, I don't know what that thing is as a fraction. Just hit the fraction button, and it tells you that the decimal 0.83333 converts into the fraction 5/6. It'll just tell you that. So you don't have to worry about it too much. It'll do it for you. So just divide the pi out, and it'll tell you what. So this is 5 pi over 6. You took the pi out, put the pi back in. It's 5 pi over 6. Or you can just do the simple conversion. That's not too difficult. So we're going to move on and look at the rest of these. So we know that in degrees, the answer was 150 degrees. So we have 150 degrees is an answer. Okay. So we know that theta equals 150 degrees is an answer. Now, remember that arc cosine, this guy right here, gives us answers in quadrant 1 and quadrant 2. Okay? This thing gives us answers in quadrant 1 and quadrant 2. This thing right here is in quadrant 2. But we know that there's another answer between 0 and 360. We know that there are two possible answers. How do we figure out the other answer? Well, that takes just a little bit of work with a unit circle. So let's scroll down here and get this by itself. And let's look at the unit circle for just a second. And let's think about this. Now, obviously, if this thing right here is on your sheet, there's no reason to go through all this. You just look it up on your sheet and you're done. However, sometimes that value isn't on the sheet. What if that were negative root 5 over 2? Or negative root 2 over 3? That's not on your sheet. You can't just look that up. You have to do it this way. I'm showing it to you right now, and I'm going to show it to you a bunch more with angles you already know, so that you get the process and you can verify it. So let's look at this. This is the unit circle. It's going to be my unit blob here. Perfect. Killer. And what we have is a 150 degree angle. So something like that. That's about a 150 degree angle. So that's a 150 degree angle. Okay. And what we're asking about is cosine, this distance x, that is literally, I'll do it in green, that is literally this distance right here away. It's that distance away. I can do it in green though. It's this distance away. We're looking for this distance. So the distance is right there, but the other one is going to be down here. So there's these 2 points. All right. So this is negative root 3 over 2. Okay. And for the purpose of this problem, we don't even care what that is. Of course, you know it to be 1/2. But the other one is going to be down here. And this is also going to be negative root 3 over 2. Because remember, cosine is x. These both travel, look here, they both travel the same x distance. Then one goes up and the other goes down. How do you find this angle to get you all the way down to here? How do you find that angle right there? How do you find that? And this is just the exact same math that we've done over and over and over back a few sections ago. So in order to find that angle, which thankfully we're working with this, you know that this distance, which I'll do in a bright pink so that you can see it. So you know that this distance right here, is going to be 180 degrees. That gets you halfway around the circle. Okay. Plus this distance right here. Because you know that these two, let's say orange distances are the same. The distance from here to here is the same as the distance from here to here. You know that. So you're going to say it's 180 degrees plus, let's do it in pink again, 180 degrees plus whatever that angle is. So what is this angle right here? Well, this angle is 180 minus 150. 180, which is the whole thing, minus the 150 you've already went, will give you the rest of the distance. That's 30 degrees. 30 degrees, which you know to be 210 degrees, which is your other answer. Now, that's probably overthinking things, though. You know that you go around 180 degrees to get to right here, right? You need to know how far this is. You know it's the same distance as here to here. And you know that that's 30 degrees. That has to be 30 degrees because you went around 150 and the rest of this will take you to 180. Throw that up there in your head and let it do the work. 210 degrees will get it to you. And that's your other answer. So theta equals 150 degrees and 210 degrees. And those will be your two answers if you want to put them in set notation. Okay? Now, let's do a bunch more of these. But we're going to just use the sheet when we can use the sheet. And we'll come back and hop on this and look at it again when we need to. So let's look at a few more. So this one says, find all angles in one revolution of the unit circle that solves the equation tangent of theta equals square root of 3. Of course, if you look on your sheet is defined for this exactly. So it's just a matter of looking on there and figuring out when tangent of theta equals square root of 3. So if you want to use your calculator for this, you can. Tangent is very nice for this. If you have that tangent of theta equals square root of 3. If for whatever reason you do have a calculator or a phone, but you don't have your sheet with you, this is a good way to do it. Then you know that you take the arctangent of both sides. So the arctangent of the tangent cancels. And you get that this is the arctan of square root of 3. Well, we can just type that in to our good old calculator here. So let's clear that out. Could have just hit one button and done all that. But we're going to type in the arctangent, which is like that, of the square root of 3. Now, I'm going to type in on my keyboard SQRT, and it'll do square root of 3, and it'll tell me it's 60 degrees. 60 degrees, right there. It'll tell me radians too, but that's not too useful. Again, if you want to know it in radians, using this thing, you need to take the pi out, and then smash your fraction button, and it'll tell you that it is 1/3. So pi over 3 is the same thing. If you want to know it in radians. But we don't, so let's not. So there we go. So the inverse tangent of square root of 3 is 60 degrees. So we know it's 60 degrees. So we know that this is 60 degrees. And you'll notice that it gives us that an angle is an angle. That makes sense. But we want all of the angles where that happens, where the tangent of theta equals square root of 3. And we know that tangent is a symmetrical function. So we know then that the tangent function here on the unit circle, and I'll show you the unit circle, and you just got to think about the unit circle. Do a lot of thinking about the unit circle. That's kind of what trig is. Okay, that at 60 degrees, it has that property, that it's square root of 3. So up here at 60 degrees, it has that property. So you know these coordinates here are, of course, 1/2 root 3 over 2. So you know that the only other place that the sine can be positive is if you have, because tangent is a sine over a cosine, it's a function divided by another function. It's literally this coordinate divided by this coordinate will give you root 3 over 2. You know the only other place it can happen is when it's negatives, that is down here. So the question becomes, you know that this is negative 1/2, negative root 3 over 2. The question becomes, what is this orange angle here? What is this orange angle here? And then this is when you kind of go back to geometry class and remember that this angle right here, look at that. These are alternate interior angles. You know that that is 60 degrees. And you know that this red angle here is 180 degrees, because of course it is. So then this whole thing is this 180 degrees plus this 60 degrees that you know. And we know that 180 degrees plus 60 degrees equals 240 degrees. Of course, the easiest way to do this would be just look it up on your sheet, because that's on your sheet. Okay, that's all that there is to that. So let's look at a bunch more of these, and if it's on your sheet, it's on your sheet. So find all angles in one revolution that satisfies, oh, here's one where we're going to have to do it by the book. Because look on your sheet and see if you can find root 11 over 5 somewhere for cosine. You're not going to find root 11 over 5 to cosine, but you are going to know some things about that number. So there's a couple of things that you need to figure out first. The first thing that we want to do is solve this thing for theta. So to solve this thing for theta, we have that cosine of theta equals square root of 11 over 5. Okay. So then theta, take the arc cosine on both sides, is arc cosine of root 11 over 5. The first thing you need to know is this number between negative 1 and 1? If this number is not between negative 1 and 1, then you cannot do this. So that's the first thing that we're going to check. Is root 11 over 5 between negative 1 and 1? So root 11 over 5, let's type that in. So SQRT square root of 11 over 5, it is. Okay, so we can do it. It's 0 point something or negative 0 point something. And so now what we want to do is find the inverse cosine of it. So I'm just going to cut this real quick, and I'm going to say inverse cosine, go. And it wants it in degrees. So there it is. It's 48.446. And it said to the nearest tenth, so that's 48.4. So 48.4 to the nearest tenth. So this is about, we say, 48.4 degrees. Okay? But we need to find all of the angles in one revolution. And that's only one of them. And your calculator will only give you one. It won't give you the other. You have to go the rest of the way with this. So we know that the cosine function, the inverse cosine function, the arc cosine function, only gives us stuff in quadrant 1 and quadrant 2. Look back at your notes. And if you didn't take notes on this, guys, you definitely should. It's the only way I know to do these. So we know that that's 48.4 degrees, but we know for a fact that there's another thing sitting down there in quadrant 4 that's going to do it for us. So let's figure that out. And let me show you the easiest way I know of to do that. Okay? So once again, I can even go the extra mile for y'all and do this with like a tool. Let's put that right there like that. Right there like, there we go. So there's your unit circle, actually done correctly. And let's look at 48.4 degrees. That's a little bit bigger than a 45-degree angle. I'm going to do it in green. It's a little bit bigger than a 45-degree angle. So there's a 45-degree angle. So I don't know. There's 48.4. Just eyeball it. Okay. There's 48.4 degrees. And here's how you think. Here's my thought process. Okay. First thing I ask myself, and it's worth writing this down. First thing I ask myself, this is the cosine function. So it is x. It is the x. So I'm dealing with x distances, therefore. So here's the x distance. And I'm going to do the x distance in pink, or this purple. So here's the x distance. The x distance is to right here. Here's the x distance you have to go. Here's the x distance you have to go before you hop up to get here, right? This x distance you can also, though, hop down and get right here. And it's going to be the same x distance either way. X distances are what we're dealing with, so this is going to be another solution. Okay? This angle right here. The angle that is made, and I'll do this, the angle, I guess, in white. The angle between the center and here, this is the angle that we want. Okay? We want to know this angle right here. We know that this angle right here is the exact same, so I'll draw it in green. We know that this is 48.4 degrees. Just look at the geometry, you know that that's 48.4 degrees. It's negative 48.4 degrees if you measure correctly, but it's, in terms of measurement, 48.4 degrees. We know that the entire distance around like that is 360. So if we do 360 and we subtract from it the 48.4 degrees that we know this to be, right? We have the whole thing, but we take this part right here out, then we have the rest of it that isn't bolded. So that's the idea. We take 360 degrees worth of angle rotation, so we rotate all the way around, and then we take out the 48.4 bit that we know to be right here, and look at the remaining white part. That's the angle that we want right there. So all that we're going to do is 360 degrees minus the 48.4 degrees, and we'll get ourselves an answer. So 360 minus 48.4. So we'll do 360 minus 48.4. Or, if you've already got this in your calculator, just leave it alone and do 360 minus in front of it, and it's done. 311.55. You want to round that to the nearest tenth? 311.6. 311.6. So 311.6 degrees is the other answer. So the other answer is 311.6 degrees. Now, you may ask yourself, why didn't you just say negative 48.4 degrees, Mr. Bryant? Why didn't you just say that? Because negative 48.4 is less than 0, and your theta has to be between 0 and 360. That is, for this problem, it has to be positive. Cool. So that's what we're dealing with. Keep in mind that your angles will be positive for these problems, and it's just the geometry of the circle. Try to figure out the missing part. There's those 4 different cases. We wrote them down earlier in your notes. Go back and look at them. Let's do another example. Find all the angles that satisfy the equation sine theta equals 3/4. So the first thing that we do is we say, okay, well then if sine theta equals 3/4, then theta is obviously the arcsine of 3/4. 3/4 is clearly between -1 and 1, so we're good to go on that. So we go slam that bad boy into our calculator and see what happens. So we come in here, we delete that out, and we do the arcsine of 3/4, and it tells us that it's 48.59 degrees. So 48.6 degrees. 48.6 degrees. And this would tell you to round to the nearest tenth. So this is 48.6 degrees. This is about 48.6 degrees. Okay? So we think about this. Sine is y. Where's the other angle at? Think about this. Let's draw a unit circle here. Okay, let's draw a unit circle here. And let's do it in, sure. Let's draw a unit circle here, best we can. Something like, nope. Something like that. Good enough. Let's draw the unit circle, and then let's put in a 48.6 degree angle. 48.6 degree angle is something like, I don't know, that's about 45, so 48.6 is about that. Just eyeball it, close enough. We know this to be 48.6 degrees. Now here's how you have to think about this. Okay, let me draw that 48.6 a little bit smaller. We'll see why in just a second. That's 48.6 degrees. This is dealing with the y, which I'll do in white. The y is here. The y is what we're dealing with. So the y is this distance. This distance. Well, on the unit circle, there's only one other thing, which is straight across here, that is also that height, because sine deals with height. And that's over here. That is, it's this angle, which I'll do in also white. This angle here is the angle that we're talking about. And since we're talking about positive angles, we have to do that angle. We want to know that angle right there. That's the question. So how do we do that? We just use some very simple mathematics here. We know this distance right here is 48.6 degrees. So then we know that the entire distance, which I'll do in red, the entire distance is 180 minus this will give us this, what we want. So we just do 180 minus 48.6 degrees, and we'll have ourselves an answer. That is how you do it. You have to set up the triangle and the unit circle and everything in it, and use the geometry of the triangles in it to go about that. That's why you had geometry before you had this class. So let's look at this. So we already have this typed in. May as well use it, and it'll take very dirty inputs like this, like my parentheses wasn't even aligned correctly, and it'll do it for you. So there you go. 131.4 is what that rounds to. So 131.4, cool. 131.4 degrees. Type them both in, and you're done. Those are the two different things. We just found using a calculator things that aren't on your sheet. And some of you all asked earlier in the years how that was supposed to work. Inverse trig functions, right? Let's look at a couple more of these. One of them that's pretty easy, and one of them that's also kind of easy, but you got to do a little bit of thinking before you can do another problem just like this one. So let's look at them. So this one says, solve the equation 1/4 sine squared theta minus 1 equals 0 for all values of theta in the domain of 1 revolution of the unit circle. Okay, cool. So the first thing you're going to want to do for this is solve for sine theta, if you ever get one like this. So we'll solve for sine theta here. So we have that 1/4 sine squared theta minus 1 equals 0. And treat sine squared theta until you've isolated it like it's its own variable. So we're going to add 1 and then multiply by 4. So adding 1 gives us 1/4 sine squared theta equals 1. And then we multiply both sides by 4 to get rid of the 1/4. So we get the sine squared theta equals 4. Okay. Now we're going to take the square root of both sides, remembering that you get a plus or minus. And that's from the very start of this video. I explained why we do that. So this is sine theta equals plus or minus the square root of 4. So then sine of theta equals plus or minus 2. I could have given you this problem as solve the equation sine of theta equals plus or minus 2 for all values of theta in the domain of yada, yada, yada. But instead I gave it to you the other way. That's fine. So now what this actually is it's just two problems. We want to solve sine of theta equals positive 2 and we want to solve sine of theta equals -2. So to do both of these, you just take the arcsine of both sides. And I haven't been writing it, but you can come in here and write it if you want to. You're taking the arcsine of the sine of theta of both sides, so it's equals the arcsine of 2. And what I said was the arcsine and the sine cancel. So I just went straight to this step. Theta equals the arcsine of 2. Similarly over here, you'll get that theta equals the arcsine of -2. Okay? Now, please do me a favor here. Pause the video and figure out how to proceed from here, because there was a step that I've said several times now that you need to check on before you do this. So if you know what's about to happen, awesome, you understand the lesson. Otherwise, you may wish to go back and review some of the stuff that I said about the domain of the arcsine and arccosine functions. So I hope you gave this a thought, because the issue with this is the very next question you ask is the input between -1 and 1? Well, very clearly, 2 is not between -1 and 1. Very clearly, -2 isn't either. Okay? But let's assume that you completely skipped that step because you forgot about it, because you didn't think it was important. And you're just going to go on over here to Delta Math, or whatever calculator it is you have, and you're going to slam in the arcsine of 2. Look at it. It doesn't even give an answer over here. Huh. Why not? Because it's undefined. It doesn't tell you that it's undefined, but it's undefined. It doesn't work there. Notice that if I give it like 1/2, it'll give me an answer, because that's between -1 and 1. But when I give it 2 or -2, it doesn't care. It's undefined. It doesn't work. So that's what you say. You say it's undefined. You just say it's undefined. Okay, you say it's undefined here. You say that it's undefined here. But let's think about why that doesn't make any sense anyway. Where can the sine of theta ever equal 2? Like, this is the value that you get out on the unit circle. What's the radius of the unit circle? It's 1. That's why it has to be between -1 and 1, because the radius is 1. The biggest number you can ever get is 1. This is 2. It's not the unit circle. It's the two-unit circle, which you might think is me being dumb, but that's an actual thing, and I hate it. But sine theta equals 2 doesn't make any sense. You can't get bigger than 1, because the radius is 1 everywhere, because it's a radius. Okay, that makes sense then. Same thing over here. So be very careful when you're doing these, that you can actually do these. Don't think that you maybe typed something in wrong, or your calculator's spitting out garbage, or you're in the wrong mode. No, you're not. Just look at this very carefully and think for just a minute before you try shoving things into a calculator. And if you use your brain instead of your calculator, you'll actually get yourself some good answers. Let's look at one more of these that's not too difficult, and then we'll be done. So let's solve the equation cosecant of theta equals -√2 for all values of theta in the domain. Look it up on the sheet. It's done on the sheet. Okay? But let's get you started on this. We're not going to finish the problem because this video's already went longer than I want it to. But I'm going to get you started on this. Let's assume that that said like the square root of -5 or the square root of -5 over 65 or something that's definitely not on your sheet. Let's just assume that it wasn't for just a second. So here's how we're going to do this. We start out with the cosecant of theta equals -√2. You can't take the arc cosecant of both sides. That is a thing that I've seen before. But it's meaningless to us because all we have to do is just a little bit of manipulation. Remember that cosecant is 1 over sine equals -√2. And then you just take the reciprocal of both sides. So this was -√2 over 1. So you flip both sides. You get the sine of theta over 1. I'm not going to write the over 1 part. Is 1 over -√2. And then you just simplify this. Bring the negative up top because you can. And this ends up being -√2 over 2. So this is asking the same question. This question and this question are the same. where is sine of theta equal to negative root 2 over 2 is the same question as where is cosecant of theta equal to negative root 2. If you got to this point and this wasn't on your sheet, you would then proceed like normal. You would take the arc sine of both sides, so theta equals the arc sine of whatever was here, which of course it's on your sheet, you're not going to even do this part, but if it weren't, you plug it in and then you do the rest of the math. And if you want good practice, because you can just look this up on your sheet, go ahead and finish this and see if you can get the same answer. But that is actually where we're going to leave off for today. So for these, if you have cosecant, secant, or cotangent, go ahead and use these reciprocal identities, which, just in case you forgot, I'll write down for you one more time. So the cosecant of theta is 1 over the sine of theta. It's the exact same thing if you switch the cosecant and the sine. Sine of theta is 1 over cosecant. The secant of theta is 1 over cosine. Okay? And the cotangent of theta is 1 over the tangent. Okay? Keep those in mind. Okay? Those are called reciprocal identities because they're reciprocal. You can also flip these two functions. So the tangent of theta is 1 over cotangent of theta, and the cosine of theta is 1 over secant of theta. Just use these three in particular that I've written down to solve problems that involve anything on the left-hand side over here. And get it to where you need to, and make sure to check before you start jamming things into arc functions that it's going to work out. For sine and cosine, you always need to check. For the arctangent function, it's just always going to work. So for arctan, it's always going to work. We like that. But for arcsine and arccosine, they're squirrely. Make sure that what you're plugging in is between -1 and 1. It can be -1 and it can be 1. So that's it. We're going to move on. We're going to do some more practice on this. And I'll see you all back here in the next chapter because this, well, it's the end of chapter 6.